Wonderful. So we are the Society for Promotion of Science and Technology in India, SPSTI in short. I am Professor K.A. Dharamveer, a physics professor, and I'm so glad to see so many young children interested in my subject. So thank you all for coming here, the school children, the teachers who have brought the children, people who have organized for these children to come. There are a couple of other societies who have facilitated that. So thank you, everybody. And before the lecture starts, I would request Professor Arun Grover to give opening remarks and a brief on the occasion and on SPSTI's public lectures. Professor Grover.
So good morning all. On behalf of the SPSTI, Aiza Mohali and the Chandigarh administration, it's my privilege to welcome the distinguished speaker, Professor R.F. Babul, the session chairperson, Professor Kulinder Pal Singh, and the audience comprising school and college students, their teachers and parents, and the enlightened citizens living in and around Chandigarh for today's public lecture on the story of universe in this very prestigious auditorium of our city. Today's event is the fourth public lecture that the SPSTI has organized in the Tagore Theatre. The first three lectures were delivered by neuroscientist Professor Meghang Soor of MIT, USA, Professor Dinesh Singh, mathematician, the former Vice Chancellor of Delhi University, cosmologist Professor T. Padmanabhan of IUCAA, Pune, but all these were before the lockdown era. After a long gap, the president of SPSTI, Mr. Dharamveer, has taken the initiative to recommence the popularization of science activity via the public lecture in the Tagore Theatre in partnership with Professor Jasjeet Pagla of Aiza Mohali. SPSTI proposes to host at least one public lecture from now onwards in the Tagore Theatre annually. Today's lecture is also a tribute by all the institutions located in the Chandigarh region to the legendary scientist, educationist, and the nation builder, Dr. Krishnaswamy Kasturirangan, who passed away 10 days ago at Bangalore at the age 84. Dr. Kasturirangan, 1940 to 2025, has been a titan in the league of other titans of science in independent India like Homi Bhabha, 1909 to 1966, Vikram Sarabhai, 1920 to 1971, Satish Dhawan, 1920 to 2002, Raja Ramanna, 1925 to 2004, Yashpal, 1926 to 2017, M.G.K. Menon, 1928 to 2016, and U.R. Rao, 1932 to 2017. The space program of India was initiated by Homi Bhabha within the Department of Atomic Energy in 1962, and he only inducted fellow cosmic ray physicist Vikram Sarabhai as a member of the Atomic Energy Commission the same year. After Bhabha perished in the plane crash in January of 1966, Vikram Sarabhai stepped into the shoes of Bhabha. As Sarabhai passed away suddenly in sleep on December 31, 1971, the aeronautical scientist and director of Indian Institute of Science, Satish Dhawan, was asked to head the Independent Space Commission of India in 1972. Kasturirangan had obtained his PhD in cosmic ray physics working under Sarabhai at Ahmedabad in 1972, while being a part of the space research program. Cosmic ray physicist Yashpal moved from TIFR Bombay to Ahmedabad in 1972 as the director of Space Applications Center conceived by Sarabhai. Satish Dhawan, Yashpal, UR Rao, Kasturi Rangan. They all worked together for India's Space Research Organization for long years. Bhaba's protege, Ramanna and Menon, were inducted into the Rajya Sabha after their superannuation from government service. Likewise, Yashpal was appointed the chairman of UGC and he completed his tenure as Secretary DST. Yashpal remained engaged in devising policies for higher education in India thereafter. Kasturi Rangan followed the paths of all his mentors after completing his innings as the chairperson of the Space Commission from 1994 to 2003 after UR Rao. Kasturi Rangan served as the director of the think tank National Institute of Advanced Studies, Bangalore, whose first director was Ramanna. Kasturi Rangan served in the Planning Commission as well, like MGK Menon. He was a member of Rajya Sabha from 2003 to 2009, chair of the Governing Council of Indian Institute of Science, Bangalore for a decade, and a member of the TIFR Council of Management for over 2 decades. He had the distinction of working with 6 Prime Ministers of India. His last significant contribution has been the enunciation of New Education Policy 2020, where he carried forward the agenda left over by Professor Yashpal. So I am very happy that we are paying tributes to Dr. Kasturi Rangan today via this public lecture. Thank you very much.
Thank you, Professor Grover, for giving us that wonderful introduction to India's space program. And we join everybody in paying tribute to Dr. Kasturi Rangan. I now request Professor Bagla. Professor J.S. Bagla is from IISER Mohali, a very distinguished astrophysicist himself. In fact, he initiated this lecture. So Professor Bagla will presently introduce Professor K.P. Singh, who will preside over this. Bagla.
Good morning, everyone. So I'll be introducing Professor K.P. Singh, Professor Kulinder Pal Singh, who is presiding over the function today. His early education was in Punjab, and then he went to TIFR, Tata Institute of Fundamental Research, for his PhD. He worked on X-ray astronomy. He has continued to work on that theme, going from strength to strength. His last major accomplishment before he retired at the Tata Institute about 8 years ago was successful commissioning of the soft X-ray telescope on board the AstroSat satellite. While he has continued to work on X-ray astronomy, various aspects of X-ray astronomy and astronomy, he was always at the forefront when trying out new things. New technology for doing astronomy was considered. He's one of the few people who used the UT synthesis radio telescope. He was also in the group which introduced charge coupled detectors, CCDs, along with telescopes in India, and always came to learn new things, teach new things, and talk about new things. So this is my introduction to the very young Professor K.P. Singh, and now I invite him to take over and introduce the function.
Thank you, Jasjit, for wonderful introduction. Good morning to every one of you. So I hope you will enjoy this lecture on the universe. And I just want to say a few words about what future holds for you people, and where you can contribute going forward, after this lecture and so on. So everyone, boys, girls, ladies, gentlemen, welcome here. It gives me great pleasure to welcome you to this public lecture by Professor Arif Babul. He's a renowned astrophysicist from Canada. Astrophysics and cosmology deal with the study of the universe. The vastness and diversity of this immense universe has always attracted the humanity from the beginning of, let's say, consciousness in the beings. It's a multidisciplinary science that involves modern telescopes on ground and in space with new technologies. By new, I mean using new sensors, new imaging devices, new cooling systems, telescopes, control systems, satellites, rocketry, just to mention a few. Okay. It also involves big data in the terms of data storage, data compression, data dissemination, and as you will hear today, it also involves computer simulations of the slices of the universe using supercomputers that you'll learn about today. India has many indigenously developed facilities for research in astronomy, in space, and on ground. We have our first X-ray and UV observatory, AstroSat, which was also had a contribution from Canada, which is working in space in a low Earth orbit, just 600 kilometers around the Earth, and for the last 9.5 years, and for which we made a lot of things in Tata Institute of Fundamental Research in Bombay. There is a solar observatory in space called Aditya. There's an X-ray polarimeter in space, which was launched last year. These are made in India and launched by ISRO. And you heard the chairman about, our tributes to the chairman, Kasturi Rangan, who actually initiated many of these experiments during his tenure about 15 years ago. On ground, we have Giant Meter Radio Telescope in Khodad near Pune. We have optical telescopes near Nainital, Mount Abu, Hanle, in Leh. There is a solar observatory in Udaipur. And there is a very big gamma ray observatory, one of the largest, in the second highest gamma ray observatory in Hanle, around 4.3 kilometers up, in the mountains. India is also participating and collaborating in some of the large international projects in astrophysics. There is a square kilometer array in radio astronomy, which is coming up in South Africa and in Australia. And India is a big participant of that, an official partner. There is also a 30-meter telescope being built by Caltech. And India is actually contributing along with China, Japan, and US, many mirror systems and so on. We are also setting up a gravitational wave study experiment called LIGO, which is coming up in Nanded and by the Atomic Energy Department. At the same time, ISRO is engaging the entire astronomy community within India for the next generation of UV and X-ray telescopes in space, and there's a large working groups on that, and Jasjeet is a member of many of these. So the future is bright for all of you if you want to, be in astronomy, and which is multidisciplinary, as I said. So whether you become scientists or engineers, become physics, chemists, you can all be part of this exciting world and the study of the universe and so on. And there are so many projects which are going to come online soon, and you'll hear about in the news. They're already starting to work and so on, and you'll hear about some of them in the talk. So I hope many of you take up research and development in astronomy as a career as you grow up and go to your colleges and so on and beyond. And you come up with new projects to answer the many questions which we are yet to answer about the universe and so on. And today we hear about some of the outstanding problems being tackled from our illustrious speaker of the day, Professor Arif Babul. And now I request my colleague Jasjeet Singh Bagla to introduce the speaker today.
Thank you, Professor K.P. Singh. I should add that Professor K.P. Singh, after he retired from Tata Institute, joined IISER Mohali first as a visiting professor, and now he is associated with us as an INSA senior scientist. And we have a small astronomy group there, and he is the most active member when it comes to writing papers and guiding students. Moving on to today's speaker, Professor Arif Babul, who will be giving a talk on from ripples to galaxies, using supercomputers to unveil the history of our universe. He did most of his early studies in Canada with his undergraduate from the University at Toronto. Then he went on to do his PhD at Princeton University, where he worked with primarily with Professor Jeremiah Ostreicher. He did postdoctoral studies at Cambridge University and at CETA in Toronto before first taking up a job in New York University and then moving to University of Victoria, where he is at present. He has worked on many, many different aspects of astrophysics, and recently he has diversified into neurosciences and many computational aspects, including applications of machine learning and artificial intelligence. He'll be talking mainly about trying to reproduce the universe by running computer models and running simulations and then comparing them with the observations to see whether our understanding is correct or not and what are the challenges in that particular quest. He has received many, many honors. At present, he is in India as an Infosys visiting scientist, visiting professor at the Indian Institute of Sciences, Bangalore. So we kind of borrowed him from Bangalore for a few days. He is also associated, as you can see, as the Leverhulme visiting professor at University of Edinburgh, and he is also a visiting chair professor in South Africa. He is a wonderful speaker. We heard him yesterday at IISER Mohali, where he gave a slightly more technical talk on the same subject. Now I welcome Professor Arif Babul to talk about simulating the universe.
Can everybody hear me? Great. Do we have a pointer or something that I can use? Anyways, if you can get me a pointer, that would be great. I'll just start talking, and we'll start the lecture. First of all, Professor K.P. Singh mentioned many things that have happened in the last 30, 40 years in terms of technological advances, both on the telescope side and on the supercomputing side, big data science. I wanted to add one more. He mentioned it, but he didn't mention it in the context of astrophysics. Artificial intelligence and machine learning. It's completely transforming science. And you guys, you young people, this is a huge opportunity. So be aware of that. The world is about to change. The other thing I wanted to mention is that I am looking at the audience, and I feel like I should be taking a selfie with this huge audience of young people. This is fantastic, and I just want to thank you. I want to thank you for coming this morning.
Out of range. Professor Bagla is sitting there.
No. My pointer, the laser pointer for the yeah. The other thing I wanted to mention before I actually start my lecture is that I have traveled around quite a bit. I've given lectures in England, in Europe. I've given lectures in North America. And I've spent the last 3 years, this is my third visit in India, and I've spent a lot of time working with students in India. And I'm not trying to flatter you. Your training, the education that you're receiving is amongst the best in the world. And there is a huge number of scientists of Indian origin taking over prestigious positions around the world. And looking at this room and seeing how many people have come here this morning, I'm hoping that I see a large fraction of you stepping into those people's footsteps. So let me start with my lecture now. The title, as you can see, is about ripples to galaxies using supercomputer to understand our universe. And some of those words up there won't make any sense to you in the moment, but I will guide you through. Thank you very much. Yes, great. Thank you. As we go through my lecture, I'm hoping that by the time we get to the end, you will have a good sense of what it means to have ripples and going from ripples to galaxies. So could I have the next slide, please? So here's how I'm going to break down my lecture. There are basically two sections to the lecture. First, I will tell you a little bit about what we have learned about the universe from observations. Science involves doing theory work to understand whatever experiment you're doing, whether it's in the medical science field, whether it's in neuroscience, whether it's in physics. But the flip side is that theorists can come up with many stories. Ultimately, the test of those understanding, those attempts to understand, hypothesis is experimentation. And in astronomy, that's observations. We cannot restart the universe. Nobody can go back and press reset and start the universe again. But we can make observations and see how our understanding compares to what we observe in the universe. The first thing I'd like to do is just give you a sense of how much we have understood about our universe in the last 20, 30 years. So could we go to the next slide? So since this is a general lecture, I thought I'd start at a basic place. And a good point to start for my talk is the galaxy. So we live in a galaxy known as the Milky Way. This galaxy has a shape of a pizza. Think of all the stars sort of going round and round in a pizza pie. And so this is what it would look like. We, of course, can't take a picture of our own galaxy, but what we can do is we have a good understanding of what the galaxy looks like, and so this is an artist's diagram. This is the center of our galaxy. The sun is sitting just about here, about a third of the way out from the center of the galaxy. Okay, so that's where our solar system is. The sun is a star, and the sun is one of 100 billion stars in our galaxy. So could we go to the next slide? So if you go to a dark place, a place where there's no light pollution, which is getting rarer and rarer these days, but if you go to a dark place and you look up in the sky, you will see a view that looks like this. What you are seeing up there is a lot of stars. You are seeing a band that cuts across the sky, and that band is our own galaxy. Because we are sitting in the galaxy, in the pizza pie, and we're looking in and out, what we see is a band of stars that cuts across the galaxy like this. But hidden amongst the stars, there are other galaxies. And so this is an image of what a little patch of the sky would look like if you could point a telescope and look at it, and you would see that amongst the stars, there are many, many, many galaxies present. So could we have the next one? And then these galaxies themselves have different shapes. Some of them look like our own galaxy, and then the next one. And some of them look completely different. Some of them look like pizza pies, and some of them look like balls of stars. And this is an example of something that looks like a ball of stars. Yeah, actually, you were right on. Next slide, please. This is a complete sort of a picture of all the different types of galaxies that exist. What I want you to understand here is that galaxies are as diverse as human beings are. They come in every shape, every size. They have different types of properties. Some of them are blue in color because they are rapidly forming stars. Some of them have stopped forming stars and they are getting older. And in the stellar sense, in terms of color, old systems tend to be red. So red and blue galaxies, and everything in between. We have flat galaxies, pizza-like galaxies like our own. Could we have the next slide, next little clip? We have galaxies that are like balls of stars, as I mentioned earlier. These are the ones that look like our galaxy, except you can see the patterns in them are very different from one to the other. And then there are galaxies that look like smudges of stars. And so there is such a huge variety. One of the challenges that we have is not just to figure out how galaxies formed, but why are they so different? What made them so different? And so let's go to the next slide. So before I start, I do want to emphasize that when I say observers see, you heard a little bit about that in the introduction. When observers see, I don't mean see using visible light only. Visible light is a tiny little slice of a kind of radiation that we call electromagnetic radiation. If you take visible light, it's a wave, and you stretch it so the waves get longer and longer, you move from visible to infrared to microwave radiation, all the way down to radio waves. Radio waves, microwave radiation, visible light is all part of the same kind of radiation. And then if you squeeze the waves, you make them shorter, so the waves get shorter and shorter and shorter, then you move to ultraviolet, you move to X-rays, and then you move to gamma rays. So all of these radiation is electromagnetic. When I say we observe the universe, we study the universe, we look at it in all of these wavelengths. We look at them in X-ray, we look at it in gamma rays, we look at it in ultraviolet, we look at it in visible, and so on and so forth. So could I have the next slide? So this is what a galaxy like our own Milky Way would look like if you were to look at it, for example, in the optical. So this is when you take a regular telescope and point it at it, this is what it would look like, right? You see stars glowing and things like that. Then if you go to infrared, you are looking at old stars. Remember, old stars tend to be red, and so you tend to see infrared colors, and so that's what the stars would look like. In radio, this is what the same galaxy would look like. In ultraviolet, it looks completely different, and in X-rays, it looks yet different again. So again, it's not just understanding the different shapes and sizes and different properties of galaxies, but also why they look so different from each other in the different spectrum, in the different bands. Why do they look different in X-rays than they do in ultraviolet? All of this is part of understanding the universe. Okay, next slide. So I'm going to skip over this, but it's just an image of our own galaxy in the same thing. It's going from radio through infrared, through optical to X-ray. Let's continue on. All right, so this is a picture going back to the one I had shown earlier, which is a night sky. This one, I believe, is from Ladakh. This is a picture that was shown at ASI last year, and it's such a pretty picture that I had to have it for a presentation like this. It's a Milky Way band right there. You can see, and then in the Milky Way, you'll see a region where sort of there are more stars. It becomes a thicker, fuzzy region, but there's a lot of darkness in it. Now, I use the word Milky Way because that's the word that astronomers around the world have adopted for our galaxy. It looks like a squirt of milk that's spread across the sky, and that comes from, the story comes from Greek mythology. But I discovered a few years ago that in Hindu mythology, or in Indian mythology, the same galaxy is known as Chayapant, because the emphasis here is on this dark path in the sky amongst the stars. And so you can see that cultures around the world have come up with different ways of looking at the sky, but everybody is fascinated by the sky. But sky is even more important in the sense that in the olden days, it was how we navigated around the world. We used the stars to guide ourselves through the ocean, through deserts, and then we also used it for timekeeping. We used it for keeping track of when is the planting season and when is the harvesting season. And a lot of our great festivals are, the festivals that we celebrate today are associated with those events. Let's continue on. Now, I mentioned that there is this region here that thickens up and has a dark, both dark and light here. that is the center of the center of our galaxy. And so we can actually look, think about sitting in a pizza slice, facing the center of the pizza and looking at it. And that's what we're seeing. We're seeing the center. And in the center, there is a gigantic black hole. And if you've seen the movie Interstellar, you will know that I have stolen this image from the movie Interstellar. It's actually a very realistic movie of what a black hole would look like. It's a black hole is a very strong gravitational region with such strong gravity that everything has collapsed in, and all the gas around it is swirling and falling in, and so this is the gas that's swirling and falling in. In fact, it turns out that every galaxy in the universe has a big black hole in its center. And when I say big, I mean like our own is about 1 million times the size of our sun. And typically, galaxies have black holes that are size of 1 billion times the size of our sun. So these are massive, huge objects. How do they form? Why are they sitting in the center of our galaxy or centers of all the galaxies? And what have they done? Like, what is their effect? All of this is part of the questions that we would try and answer. So let's go to the next slide. Maybe I'll wait for a second while the new student group that's coming in will just sit down. While we're waiting for them to sit down, I don't know when exactly we started, but can somebody give me just 11:20? So can you give me a sort of a sign or something when we're reaching 11:50? No, but I will, but I just want to know where I am in terms of time. So just give me some mark or something at about 30 minutes from now. Okay. Yes, yes.
Please sit down quickly. Sit on the steps. Steps together. Thank you.
Okay. All right, so I mentioned that there's black holes in the centers of galaxies, and these are very, very large black holes, very strong gravity. So strong that if something was to fall into a black hole, it's not coming out again. The gravity is so strong that even light cannot get out. So we do not know what happens inside a black hole. And now things fall into a black hole. Because of its gravity, as I've mentioned, every time a star comes too close to a black hole, the black hole will grab it and swallow it. We've actually observed this happening in the last few years. If gas is swirling around and it gets too close to the black hole will pull it in. Now, when a star or gas falls into a black hole, as it's falling in, it will radiate tremendously. It puts out huge amount of radiation, and that radiation comes out in two forms. One, it comes out in electromagnetic radiation, the kind of radiation I talked about, and the other form is very, very powerful jets. Very high, it's like a fire hose, right? Or a hose of water. I turn it on and I point it at you and you get this jet of water squirting at you. That's what it's like. There's very powerful jets coming out of black holes. And as they spread out, they affect the environment all around them. So here you're seeing black hole images, real images of black holes that are in fact firing these jets that are pouring out and coming out. So this is an artist's rendition. This is an actual image. And these jets extend out, vast differences. But not only that, black holes themselves, when they are fully engaged, they radiate more brightly than 100 billion stars. They can outshine everything in the galaxy. And we see these as quasars. So if you ever hear the word quasar being mentioned, this is what it is. These are black holes that are shining brilliantly. All right, next slide. So I mentioned that jets and energy from black holes can affect the region all around it, huge regions around it. I just want to give you a sense of what that means. So this is a galaxy. Inside that galaxy, there is a black hole in the center. You can just barely make it out. And then if you look carefully, you'll see this blue streak coming out. That's a jet. That's this fire hose of high velocity gas that is pouring out of the black hole. And it doesn't look like it's going very far, right? Maybe the size of a galaxy. Okay, next click. This is what it really looks like when you look at it in radio. So you can see that it has affected a huge distance around it, literally changed the environment around it. And that environment is roughly about 4 times the size of the galaxy itself. So things fall into a galaxy. Galaxy has its own processes going on, but that process of galaxies will then change the environment around it, and then the environment will then affect the galaxy. So, when parents are talking about raising children, there's often this discussion going on. Is it nature? Is it your genetic stuff that's making all that's important? Or is it nurture? Is it the kind of environments that the parent create for you that makes a difference? Turns out in nature, both play a role. And in the universe, we see this vividly. Galaxies are affected by nature, also by nurture. And this is an example of nature taking effect on the situation around it. All right, next. Now, I've talked to you about individual galaxies. Let's ask the question, if I look at the universe, what do the galaxies look like? How are they spread out in the universe? So this is an image from a survey. It's a 2-mass survey showing the dots on here are not stars. Each dot is a galaxy, with the exception of this bright band in the center that's our own galaxy, which we can't sort of remove. Each of those dots up there is a galaxy in and of itself. Each dot is about 100 billion stars. Now, if you look at this, it looks really smooth. It looks like it's all spread out evenly everywhere. But let's look at it more carefully. So let's go to the next slide. What you're about to see is my colleagues taking images of how far away it is. It's like me taking a picture of this room and everybody looks like they're close to each other. Just everybody looks like they're on a sheet of paper, flat, right? But if I could figure out who's in the first row, who's in the second row, who's in the third row, who's in the last row, I can make a map of what this auditorium looks like. And then I can figure out who are the friends and who are sitting together and why is there 2 empty chairs sitting there, things like that. What you're about to see here is an example like that. Some of these slides are a little on the dark side, but hopefully, yeah. So you can see here these chains. So galaxies are not spread out evenly. They are distributed across the universe in big chains. It's like a necklace. Everywhere there are necklaces where the galaxies themselves are like jewels in the necklace. They're twinkling, they're bright, but they are spread out in these large necklaces that are organized across the universe. And then where there is no galaxy and no jewels, you will see empty regions. So you can see here, there's these huge empty regions. So the universe is not uniform, it's not homogeneous, it's not the same everywhere in every direction. It is very different. There's organizations. If you study the human body, it's like how the blood vessels are organized. Blood vessels have their own little paths that they carve through the body, and rivers also do the same thing. You don't have water everywhere. You have water in the rivers as they flow towards the ocean. In the same way, the universe has all the galaxies are organized in these streams or filaments, as we call them. So let's go to the next slide. When I put all of this together, this is what it looks like. Now here, this is all the galaxies. It's like taking a picture of this room, but I have color-coded. People in the front row are violet. People in the back row are green. And so I've mapped out everybody on this one image, and you can see that there are different colors, and galaxies of different colors belong together, are sitting in these chains like this or like this. Okay, let's go to the next slide. Now, where these filaments meet, it's like rivers meeting together. Where these rivers meet, you have a confluence. You have concentration of water. Here, we have a concentration of galaxies. And so you have huge regions where there is thousands of galaxies that are sort of pushed together. And this is just two examples of such concentrations that we call clusters of galaxies. These galaxies, because they have been pushed together, they are trapped by their own gravity. And so they are whirling around more or less the way you see them here, trapped by their own gravity. They're moving thousands of kilometers per second. And yet, they are not flying apart. There is strong gravity holding them together. But one of the questions that we have to tease out is, how do these structures form? How did the universe form these filaments that stretch out hundreds of billions of light years? Now, does everybody know what a light year is? Yeah? Okay. So, just to get a sense, if something was to happen at the sun today, right now, how long would it take before we find out? Perfect. So you guys know the answer. Excellent. So what we're seeing here is structures that are not 8 light minutes away. We're talking about hundreds of billions of light years. So it also means that when I look at a galaxy far, far away, I'm not looking at it the way it was today. I'm looking at it the way it was when the light left that galaxy. That could be 10 billion years ago. That could be, 13 billion years ago. Okay, let's go on. So this is a map, sort of a schematic diagram of what that looks like. As we just discussed, light takes a finite amount of time to cross distances. It has a speed of 300,000 kilometers per second. And so if this is the Big Bang, where the universe began, and this is where we are today, when we look back at the universe, the further we look, the further back in time we're looking. So in that sense, you can think about telescopes as being time machines. Every time you look at something further away, I'm actually looking at the universe the way it was back in time. And so the Hubble Space Telescope managed to go back, making images and telling us what the universe was like about 500 billion years after the Big Bang. But with the James Webb Space Telescope that's up there right now, taking fantastic, impressive images of the sky, what we are able to do is detect the universe, observe the universe as it was roughly about 300 million years after the Big Bang. That's a very short time in the history of the universe. And when we look at that, what we find is that there are already galaxies present. Already objects that are starting to resemble our Milky Way. And the fact that they have formed that fast is a puzzle. Trying to understand why, how they formed that quickly after the Big Bang is proving to be a challenge for us. Okay, let's go on. So this is again the same image. And here what I'm trying to answer the question, if I keep looking back and I look back and I look back, what's the furthest I can look back? And it turns out that the furthest we can look back is roughly about 375,000 years after the Big Bang. What we're seeing here is the microwave background. So when the universe was born, there was a tremendous amount of energy that was released. That energy eventually, over time, cooled down as the universe expanded. And as it cooled down, today it's in the microwave regime. So you guys are very young. You probably don't even know. But when I was a child and you turned on a TV and there was no station, you would get this static. You would go shh, and there would be this a fog pattern. In fact, it's only later on when I was in university that I was taught that what I was observing was the microwave background. So this is, radiation from the Big Bang. It fills the entire universe, And that's the furthest back we can see. And we have telescopes that can do that, both space-based telescopes and ground-based telescopes that can study this radiation that's coming from basically 375,000 years after the Big Bang. So we can go that far back. Now, let's go on to the next slide. This is the image of the microwave background. Now, I'm not showing you the exact image that you would see. I'm showing you the image that is slightly processed, but the important information is in these images. So this is an image that was taken in 1992 when I was in graduate school. And it's the first image of the microwave background that's showing ripples in the microwave background. And then over the years, there have been satellites that have gone up and taken more and more precise. You know, remember we heard that technology has improved. We can take very precise, very high resolution. It would be equivalent for me to sort of take a picture of the images and sort of smear out everybody. 3 or 4 people get smeared out together, and I can't tell who's who, but I can know that there are people sitting there. That would be this one. This is like an image where I can actually see each individual person. And so this is a high-resolution image of the microwave background. And again, you can see that there are hot spots and there are cold spots. Now, what is this all about? Turns out that when the universe was born, as it was expanding in its very, very early times, matter in the universe was not completely smooth. There were tiny little ripples. So when I say from ripples to galaxies, this is the kind of ripples I'm talking about. Now, to get a sense of what a ripple is, if you filled up a bathtub, if you filled up a bucket of water, and you just let it sit there while it's absolutely still, so there's nothing moving, the surface of the water is completely still. Pluck out your hair, drop it on the water, it's floating there. Now the question is, can you walk back 1 kilometer and see your hair? That's the question. That tiny little ripple caused by your hair being observed at 1 kilometer, you would say it's impossible. That's what we're doing here. We're observing ripples that are, relatively speaking, as small as the width of your hair in the early universe. So when I say ripples, I'm talking about tiny little ripples. It's almost like if I was to blow out in the air, it gets a little bit more air molecules here. That would be too much. That would be too big a ripple compared to what we're observing there. But the universe had these tiny little ripples. And that's the starting point for the story. The exact ratio was given up there, 1 part in 100,000. Yeah, let's go to the next one. So the challenge, now we move to the second part. I've told you what the universe looks like. I've told you what we have learned. Now the question is, can we make sense of it? The question really is, if I start with these ripples, tiny little ripples, can I go from there to there? Can I capture these images where the universe has filaments and voids? Or can I capture images where I have clusters of galaxies and I have galaxies themselves? Can I understand how galaxies formed? Can I understand what the black holes did to the universe around them? How did they shape everything? How did these structures that I've just described as filaments, how did they come about? How did we go from tiny little ripples to a universe that looks incredibly structured and organized, and as galaxies organized like necklaces on a jewel, as I described earlier? So let's go to the next slide. So the question then, one of the questions that comes up is, but why? We can observe the universe. We've seen what it is like, so why do we need to do anything now? And the answer is, if I was to take an image, and this is what astronomy does, it takes images of the universe at different times, and you see change going from one place to the other. If you don't know what's caused the change, if you don't understand the physics, if you don't understand the astrophysics, you're not going to be able to figure out how the change happened. So to illustrate that, consider this image. This is an image of the Arctic, of a region in the Arctic taken 103 years apart. So this was about 103 years ago. You see glaciers filling this landmass right here. And then today, if you were to take that same picture, this is what it would look like. So having two different pictures doesn't tell you what happened. Okay, you can say the ice melted, but how did the ice melt? Did it all melt all together really fast, like in 6 months? Or did it happen gradually? In order to make sense of that, we have to understand the physics. So the challenge of people like myself who are astrophysicists is to understand how all this happened. How did this change actually occur? Okay, let's go to the next. So the starting point is we know that there is gravity in the universe, and we know that matter responds to gravity. So that's the very first thing. And so what we do is we can take a huge box and fill it up with matter and make it, sort of look like the universe, and then just simply put it on a supercomputer and let the particles respond to gravity and move around, and they'll speed up and they will organize. And we can ask the question, what happens if you do that? Now, as I said to you earlier, we cannot go back and press restart. We cannot set the Big Bang in motion again. But what we can do is we can put this on a supercomputer and repeat this. And just as Europe and North America, Canada, United States are in the game of doing this, so is India. India has gotten some of the fast supercomputers over the last few years, and there are a huge number of astrophysicists who are working on these problems. One of the reasons why I'm at IISc is because I'm working with a collaborator who's one of the world's leading experts in this area. And together we are able to combine our expertise to push the field forward. So, again, I emphasize that not only is the education here excellent, you have some of the best universities in the world, and the research that's being done here is right up at the cutting edge with LIGO, with the 30-meter telescope. There is a huge scope of opportunities available all around. And now the question is, if you start with this box and you let it run, and you let it run for an equivalent of 13.7 billion years, which is the age of the universe, what happens? So let's go to that. So this is a box. Now, can you go back before and not start it first? Can we just back up? Yeah. Go back one slide. Yeah, right there. Just stop it. Okay. Now, I guess it's starting on its own. If the box was stationary for a second, you would have seen that there were these blue smudges. Those smudges are regions where the ripples are a little bit stronger, and then the black regions are ripples are a little bit weaker. And now you let gravity start moving, doing this magic. Can we just repeat this slide again? Yeah, so you can see these ripples. These ripples are slightly blue, and now you let it start running. And what you see is regions where their ripples are a little bit stronger. There's a little bit more gravity. And they start pulling things together. And so as they pull things together, that region becomes more and more dense. And if you do this over 13.7 billion years, or in this case, we stopped it at 11 billion years, what you see is a universe, virtual universe, that starts to look like the real universe. It has matter that gets organized into filaments with galaxies strung out along the filaments. And then you have voids, and you have regions. Okay, can we play this again? Great. So you can see the structure starting to form, and you can see these spaghetti-like filaments starting to form throughout the universe. And then where the yellow dots are, that's where galaxies and clusters of galaxies are starting to form. So we are with ordinary matter and just gravity, we can actually start to form things that resemble the universe. But there is a little hiccup here. The hiccup is that universe doesn't just respond to gravity. What I'm forming is stuff that looks like a galaxy, but it doesn't really resemble a galaxy. If I want to make something that looks like a galaxy, I need to throw in a little bit more physics. Now, you're familiar with ordinary matter like ourselves. The room is full of ordinary matter. You and I are made of ordinary matter, and we are radiating. If you touch your head or your hand, you'll see that you're warm. You're radiating energy away. This is why ultimately you'll get hungry and then you'll have to eat to replenish the energy that you're using. You will move around and you will use up energy. So we have to worry about this extra physics that's coming in, where as matter comes in and it radiates energy, what happens? It cools down, it heats up. How does that change everything around it? So let's see. Okay, so first of all, before I even start complicating things, if I just take the image that I just made, the box, and I make a map of it, and I compare it to the real universe, I think you will find that you are hard-pressed to tell the difference between these. These two here are simulations of the kind I just showed you, and these blue maps are real universe. So the large-scale structure of the universe is coming out right. We can get that much just straight from gravity and the ripples that we have observed at the beginning of the universe. Okay, now let's go one step further. We know that the universe isn't just made of stuff that responds to gravity. Stuff responds to radiation. Ordinary matter like ourselves, when you squeeze it, it heats up, it radiates, it cools down, it glows, it has pressure, right? When you fill up air in the balloon expands. In the same way, all of these processes have to be accounted for. They all play a role. So let's go to the next slide over. So what I want to do is get to this. I want to be able to make a galaxy that looks like our own galaxy, or like this, our nearest neighbor galaxy, Andromeda. Let's go to the next slide. And the amount of physics that I have to put into the simulations now becomes infinitely more complicated. First of all, okay, the number of physical processes has already grown. And in addition to that, these physical processes like fluid, like how water flows is a complicated process, like how black holes form is a complicated process. Stars explode and they throw energy out. That, all of it, is a complicated process. But we have to put it into these simulations, and that's where life becomes difficult and challenging. And when I say that today we have made a huge leap forward, I can also tell you that what we have done in many ways, this huge leap forward, is equivalent to scratching the surface. There is a huge amount of physics that still needs to be resolved, and we don't have the computing power. What we need is creative people like yourselves to figure out smart ways of working around the challenges that we're facing. This is what my graduate students do today. They know that the computers are not powerful enough to do everything. So we have to figure out smart, creative ways of solving the problem and still getting the right result. Okay, so let's go to the next slide. So I'm not going to go through this. It's just up there for you to sort of glance at it and see that there are so many complicated processes that we need to worry about, that even the fastest supercomputers in the world can't do all of these things completely accurately. So let's go to the next one. Now, I put everything together and I let it run on a supercomputer, and these are the kinds of images that you come. Is it possible to just turn down these lights up here for a second? Yeah, thank you. So what you're seeing here is one of these big boxes with all the physics that we understand and all the physics that we can physically put into a computer running, and then of course the image is rotating because it makes for a nice pretty picture, right? It makes for a nice video. But what you're seeing is galaxies, these chains of galaxies forming. You see galaxies forming here and here. Wherever there is lighting, things light up, there's galaxies forming. And then when galaxies have stars, when stars explode, when they die, they explode, you can see an explosion going off. And these explosions are escaping the galaxy and shaping the environment around it. You also have black holes in these simulations. So black holes are also putting out energy, and they are also doing this. And you can see that systematically over time, the whole nature of the universe is changing. You can see that universe started out with little pockets of stars and galaxies forming and everything else being cold. And now, as time went on, almost all of the universe volume is hot gas. Stuff has been thrown out, and it's filling the universe like a balloon is filled with hot gas, hot air. Okay? So let's continue on to the next slide. Now, when I do this kind of simulations in detail, and I start to ask the questions, what do my galaxies look like? You start to see this. You can see that I have the ball-like galaxies that look like stars that are arranged in a bowl. I see pizza slices, pizza-like galaxies all over the place. See, they look, when you look at them from top down, they look like a flat plate or a flat pizza. When you look at it from the side, it's like looking at a pizza from side on, and you can see how thin they are. And so you can see that we can actually make galaxies that resemble galaxies in the real universe. We can, in fact, capture 90% of the properties of the galaxies correctly. Let's go to the next slide. But in spite of everything that I've told you about how well we have done, there are still challenges left because the physics that we're trying to capture is complicated. And at some point, you have to make choices. So these are results from 4 different groups. I'm associated with the SIMBA group up here. And if you look at the outcome, not at the individual galaxies, which everybody gets the same, but if you look at the environment around the galaxies, you see that SIMBA is already heating up the universe much earlier than this group right here, or this group right here. In fact, these two are heating up the universe faster than this. This is an opportunity for us to test what's going on. We can now point our telescopes and ask the question, is the universe really that hot? And which of these 2 models or 4 models is correct? Maybe none of them are correct. If you ask me, I would actually, all due honesty, I'll say all of them have flaws in them. All of them have something that's not right, and it still needs to be fixed, and it's still very much a work in progress. And of course, that's what science is. Science is always moving forward, because we can never really rest. There is no such thing as the end product. We are only improving and improving and improving. So let's go to the next slide. What we are able to do with these new simulations and powerful supercomputers is understand how galaxies formed and appear in the universe 300 million years ago. We can do that. You may read in newspapers that astrophysicists are completely confused. They don't understand how JWST galaxies formed. What I can tell you is that the new simulations that we've done actually do that. The problem was we didn't do simulations with high enough resolution. It wasn't fine enough in the granular sense, right? When we do that, we actually get the right results coming out. So that's kind of interesting and satisfying. Let's go to the next slide. And so as I told you, we have made huge leaps in both observational side and on the theoretical side in understanding how galaxies form, how structure forms, how the universe evolves, and we know that the universe is 13.7 billion years old. So in that span of 13.7 billion years, we know how the universe has evolved in the big, broad brush sense. We even can do some detailed analysis and find that we can get it right. Have we got everything? Do we understand everything? The answer is no. And so there is a huge scope of opportunity. One of the projects that I've just started working with my colleague in Bangalore is that some of this physics that we cannot put into the supercomputers, we have figured out that we can do better with AI. So now we're starting to use AI to actually help us with the physics. So, your world is going to be transformed with all the technological development that's happening here. But science itself is going to be transformed by all the technological developments that are happening here. And in the same sense, our ability to make sense of the world around us, whether it's the earth sciences, whether it's the climate around us, whether it's the solar system, or whether it's the universe itself, our ability to grasp and understand the world around us is going to be transformed around us. And so I'm going to stop right here. Thank you very much. Are we taking questions? So, you know, I've been told that there is time set aside for questions, and I'd be very happy to take questions. Yes, go ahead.
Yes, sir.
Do we have somebody who can give him a microphone to? We had one of those microphones sitting here. Yeah, there it is. Anyways, go ahead, ask your question. I'll just repeat it for now.
From what I've understood from the lecture, I see that most of the biggest contributions that are made to the universe in terms of gravitational effect are black holes, come from black holes, right?
Well, I emphasized black holes. I wouldn't say that they're making the biggest contribution. I would say they're very important. I emphasized black holes only because we only realized that black holes were important roughly about 10 years ago.
Right.
And so this is a new ingredient in our simulations.
Right.
But yes, they do make a very important, they play a very important role and they shape the world around them.
I
Yes.
did wonder if, you know, for isolated systems of galaxies, can their motions be simplified to just gravitational problems involving just a few bodies of black holes? If you can simplify that calculation.
Yeah, so for isolated galaxies, it depends on what you want to do. If you just want to know how the galaxy is moving across space, then you are absolutely right. You can simplify the problem. You don't even have to worry about black holes. All you have to do is just treat this galaxy as one big point and work out the gravity on that. So yes, you can do that. But if you want to know how that isolated galaxy formed, then you have to model everything. You have to model gas falling in, you have to model stars forming from the gas, you have to model black hole. Then it becomes complicated. It's as complicated as doing the simulations that I've just described for you.
And just one more question, sir.
Sure.
You also said that AI has been making, you know, great leaps, has been helping a lot in the physics. From what I've understood of AI, I've seen it basically is just a more elegant form of computation. But at the end of the day, it uses previous data to make new data. But since here, the previous data that we have is basically just the laws that we already know. How is AI helping us make new data that we don't know? Isn't it using the same data that we already have?
Actually, that's an excellent question. So let me give you an example of something that we know how it behaves, but we have no good theoretical understanding of how to explain it in detail. Turbulence.
Right.
So if I take water, you know, in a glass and I swirl it, or if you watch the river as it moves and it's churning, especially if it's falling over rocks, it's churning around, or if you go to the ocean and you look at it, that behavior of water churning around, we understand it, but we don't know how to describe it in detail. It's very complicated. That's the problem. Now, what happens with AI, especially in the case of turbulence, is that I could either do simulations, but it turns out that the simulations of the kind I do is not enough. I need to have simulations that cover the big scale, like it's like covering the entire scale of this room.
It's zooming out.
And I should be able to zoom in to tiny little details to the size of a molecule. But I can't do that. I just don't have the computing power to do that. Okay? But what I can do is I can train an AI. Now, you say it's an elegant computing system, but it's actually a little bit more than that. An AI can figure out patterns and make inferences from those patterns where we get stuck with the statistics. So statistically, there is no difference between model A and model B. But AI can figure out tiny little differences and pick it up and basically magnify it. And so using that capacity to figure out what the arrangement is in a complex system, and then if I train it, I have to train it on numerical simulations. So I have lots of simulations, I train it, it learns about turbulence. I don't know how to predict it, but it figures out how to predict it. So then when I say, okay, here's the input, tell me what will happen, it will take a good guess The guess, if you train your AI smartly and well, the guess is better than the guess I will make. That's the thing. There's certain things that are so complicated that we can't calculate ourselves. But somehow, you know, the way it's structured, it can extract that information out.
Thank you, sir.
Yeah. Yes, all galaxies have black holes.
Sir, I have two questions.
Sorry, let me.
I have two questions. The first question is regarding galaxies that we observe. And you said that blue is colder and red is warmer. Now, they're also moving away from us. So there's a red shift. Now, how do you account for whether the color of the galaxy is because of red shift or because of...
No, that's a really good question. We can actually take out the expansion of the universe. We can figure out whether it's moving or not moving because of the shifts in the line radiation of the spectra.
Okay.
So once we take that out, then we can look at the color. In astronomers will say in the rest frame of the galaxy. So as if you were standing in the galaxy, now you're looking at the galaxy. Is it red or is it blue? But it's not that red is hotter. It's actually the opposite. Red is cooler. So red stars tend to be old stars that are cooler stars. Blue stars are young stars that are very hot. So if you look at the sky, for example, I think you can see it here. If you can see Orion.
Yeah.
Orion Nebula, the Orion constellation has two stars on the opposite end. One is a red star.
One is blue, yeah.
And one's blue. The blue one is young and hot. The red one is old and cold, coldish. In fact, big and cold. One day, that one's supposed to die. Yeah. It could be tomorrow or it could be next week or 10 years from now or 100 years from now. But the blue one is the young one.
Secondly, in your simulation, do you consider dark matter?
Yes, we do. I deliberately avoided dealing with dark matter, but yes, we do. It turns out that, you know, I mentioned matter in the universe. And I said that there is, you know, we are made of ordinary matter. We heat up, we cool down, we radiate. Ordinary matter has pressure, you know, or ordinary matter is also the kind of matter that you have in the swimming pool. You know, if you put your hand out of a moving car, I wouldn't recommend that you do this, but if you're in a parking lot, maybe you could do this. You'll feel a wind, and that wind is pushing your hand back. All of that is due to ordinary matter. Ordinary matter only makes up something like 10% of the total matter in the universe. The other large fraction of the matter content of the universe is dark matter. It only responds to gravity. So the first image that I showed you that was gravity only, that was a dark matter only image. But I deliberately avoided talking about that complication because it would need another 20 minutes to explain.
So, sir, I had two questions. First of all, sir, as we believe that photons are massless, so how come photons which are massless are trapped by the gravity of black holes?
So photons are massless, but they also have mass energy. And really, they're not being trapped by the gravity, but gravity, what is gravity? In Einstein's theory of gravity, gravity is the curvature of space-time, right? What we call gravity is really us feeling the curvature of space-time. What a black hole does is it makes the curvature of space-time so steep that even a photon can't get out. It's like climbing up a cliff. You climb up and you basically turn around and fall back in. That's a good image. It's an analogy, okay? Don't take it literally, but it's an analogy, a way to think about it.
So, sir, as for example, the Hawking radiation. So, sir, Hawking said that anything that go inside the black hole comes outside as radiation, but there's no the information of it. So, sir, what's your point of view on it? That anything that goes, how does it come outside?
So that's an interesting question. It's a question that caused a lot of controversy for a long time. I'll tell you what the problem is. Yes, Hawking said that a black hole evaporates. So if I throw mass into a black hole mass grows, but then because of Hawking radiation, it evaporates. So in principle, what goes in comes out. But it comes out without information, as you mentioned. But that violates quantum mechanics. quantum mechanics says you cannot put in information and get zero information coming out. So there's a whole school of people who study black hole physics who try and figure out what's happening. One of the pictures is when you add quantum mechanics to relativity, then you start to find that the region around the black hole where the Hawking radiation comes is actually not a perfect sphere. It's ripples. It's got little fluctuations on it. And that fluctuation changes the Hawking radiation from point to point to point. So somehow the information is coming out, but it's coming out garbled. So as far as nature is concerned, the information is coming out. As far as you and I are concerned, it's so noisy that we can't actually make any use of it.
Yes, sir. Good afternoon, sir. It was one of the best lectures, one of the most stimulating lecture I heard. My question as a biologist is that out of so many multiverses, so many worlds, and so many galaxies which you are observing or you are studying, ultimately, one out of that may be offering some material which is exactly like what is on this planet Earth, what is called as a Fermi's dilemma.
Yeah.
And is there anything which you find that it has a equal to that of the life on planet? Because one of the best riddles which a biologist has is to find, of course, that's the end of this research also, to find out whether the life exists at distant place, Carl Sagan's dilemma also.
Yes.
What Rangaswamy ji has also said, that the presence of K218b biomarker on this planet is equal to that of the Earth's DNA. So do you feel that out of this one possibility, there are multiverse possibility of having the same ambience as that of this one and the existence of life in a different form? Is DNA a necessity or a biological accident?
Okay, that's an interesting question that I think when I'm with my colleagues, we are continuously debating. There is evidence, comes every now and then you hear evidence that there is signatures of life in atmospheres of planets around other stars. So first of all, we have stars, and then around almost every star there are planets. And we know, for example, that a lot of the biological molecules that make up life here on Earth actually came from outer space. So a lot of the bases, if I remember correctly, 5 of the 6 bases that make up the DNA and the RNA, in fact, are known to be synthesized in space. And they were carried onto the Earth in meteors, for example. We know that chlorophyll is raining on the Earth, or chlorophyll-like molecule is raining on the Earth from outer space. So all of that tells us that the synthesis, the origin molecules of life that created the chemistry which allowed life to emerge on Earth is present in the universe. It is most likely raining on other planets as well. Now the question is, is there life on other planets? We haven't detected any. That's the zeroth order statement. If you ask me, do I think it's possible that there is life elsewhere in the universe? I think absolutely. It seems completely irrational to think that all of the raw material is coming in from the outside. It's very difficult to imagine that this is somehow a special place where the chemistry actually happened. Now the question that my colleagues and I often discuss is what kind of life? See, we keep thinking about life like ourselves. Even people who study, extraterrestrial life origin are often doing experiments where they are trying to detect kind of life like ourselves, carbon-based life. But life doesn't have to be carbon-based, could be silicon-based. Silicon and carbon have same affinity. And so they have the ability to bond in exactly the same way. And yet, we haven't actually done studies. So that's the one thing, is that I would personally say that I would expect that there is life In fact, I'm hoping that within my lifetime that there is a discovery. The question is, why haven't we actually encountered life? Space is big, and space is vast to cover. Somebody mentioned that light is massless, but light also has a finite speed. So even if something is moving at the speed of light, it still takes 4 years to come from our nearest star. The nearest star to our own is Alpha Centauri, Proxima Centauri, and that star is about 4 light years away, which means signal traveling at the speed of light will only get to us after 4 years. So spaceship coming towards us will take much longer. But who's to say that life only exists on the next star over? It could exist much further away. And then the amount of distance that you have to cover is vast. But then there is another thing. So I'm going to make I'll end the answer to your question with a little bit of a joke. I don't know how culturally relevant this is. So, America, when the first TV signals were being broadcast and the first TV shows were made, there were very stupid shows. Things like I Love Lucy or, things like that. They were sort of cartoonish, comedy, kind of silly. Now, we were beaming them out to space. So imagine aliens who are receiving our signal today at 50 light years. They're seeing TV signals from 50 years ago, and they're thinking, these guys are stupid. We don't want to go there. Yeah, well, let's not disturb them. Leave them alone. So maybe that's what's going on. Hang on, let her, and then maybe you can
Sir,
pass.
I have a very simple question, and it comes more from the psychological aspect of a researcher. Everything is so slow. And with all the research and everything that you have done in the past and for so many years, you still said that you've just scratched a wall. So how, as a researcher, you feel that is it frustrating? I know it's exciting, but is it frustrating that you've still got so much to explore and the process is so slow?
Yeah, it's interesting. It looks slow when I tell you in a public lecture, but when we're actually doing it, we're trying to solve a problem. It's only slow until you find the answer, and it's like, then it's a eureka moment, and then you're excited for about a year or two. I started my talk with the picture of a jigsaw puzzle. You think about this as a 10,000 or a million piece jigsaw puzzle. You start at one place and you start putting the puzzles together. And if you find a piece that fits here, you go, yay! And that's how it is for us. We're doing this momentary yays, but we know that the big picture will take a while to piece together. What I find fascinating is that I told you that the details will still take a while to fill in, but we have already made the frame of the puzzle. That's the amazing thing, is that in 25, 30 years, we've actually made the entire frame. We sort of know where things are going. We just don't know how to fit them in detail. So really the hard work is to come, but the hard work is a lot of grinding work. It's going to be a lot of detailed work. I was kind of fortunate. I was born and went through grad school at a time when we were right at the cusp. We weren't speculating, but we weren't also caught up in detail. I'll also tell you something that, when I was at grad school, my supervisor just passed away 2 months ago. And so I've been thinking a lot of the lessons he taught me. One of the things he taught me was, when I was in grad school, I wanted to work on the sun, do physics of the sun. And he said, no, that's not a good idea. Too much data. You will never make a theory that will fit all the data. Better to work in cosmology where there's just enough data but not too much data. So you can understand, right? So that's why today I'm saying we have to work with AI, because the system is complex. I didn't have to do that. I was still working on the big picture and understanding it's like taking a painting and sweeping across the entire canvas. Now you want to put in little dots. I'm glad that I'm coming to the end of my career. Yeah, go ahead. Yes. Yeah. Yes. Yeah. Yeah, so that's part of the debate, is that they're looking at the signatures that they think is a biosignature of life, a byproduct of life. The problem is that now people are finding that there are other chemical processes that can also make the same kind of processes. So now there's a debate going on. Is it really a biosignature, or is it simply indicating this generic class of chemical reactions taking place? But in either case, I think it's very exciting. And I think it's very important that we pursue that, because needle in a haystack is what we do. And this is a needle in a haystack. And I think it's important that we support scientists like him, because somebody has to go look for things like this. So it's very important.
Good afternoon, sir. First of all, we enjoyed your lecture a lot and we appreciate your efforts. I had two questions. First, that if we could achieve speed of light and reach the point of Big Bang, can we actually time travel in the past?
That's $1 million question. We don't have a way to travel back in time right now in a classical sense. On quantum mechanics, on the very, very small scales, we know that that's possible. Now the question is, can you, as a future scientist, figure out how to shrink yourself to an Ant-Man scale or an atom scale, go back in time, and change? Nothing would make me happier if I could open a door at home, step in, and come out in Chandigarh. Right? I hate planes. I hate traveling 17 hours. So you figure out how to curve and bend space-time, and I'll be your first customer.
Good afternoon, sir. Sir, I'm from Bhavan Vidyalaya, New Chandigarh. And first of all, I enjoyed your session a lot.
Thank you very much.
Sir, I have two questions. So first is that gravity is the driving force behind structure formation. So how can we say that? So examples?
So what do you mean by how can we say that?
Sir, like density, and sir, it depends, sir. Then how gravity, sir, it leads to the formation of structures?
Well, what happens is that it's not gravity by itself. It's gravity and those little ripples. Let me explain this to you. Yeah, so you see over here, there's an empty seats. Seats are empty, right? So if I asked you, if you were standing there, which way would the force of gravity be acting on you? Forget about the earth. Just look at your neighbors, people around you. So if you were standing in the third row in the middle, you would feel a little bit of gravity towards that woman over there. And you would feel a lot of gravity this way because this whole row is full. And so you would get pulled along. And that's what ripples are. This would be a positive ripple, that would be a negative ripple, and she would be a weak ripple. And you would get pulled towards the stronger ripple. So that's how gravity moves things around to shape the large-scale structure. Does that make sense? Okay. So density is like this. Like there's 6 people sitting here. It's a higher density. Where there is higher density, there's higher gravity. So you get attracted towards regions of higher density. Yes, matter attracts matter. I don't know how this joke would go over in India, but in America, they get very happy when I say gravity is a capitalist system. The rich get richer and the poor get poorer. It's like that. Sure.
Good afternoon, sir, and it's really nice to meet you, and it was a really nice lesson for us as we are the coming youth of our nation. And a question from you, that as we have all gathered here to talk about science, so being as the youth of our country, we have limited ourselves towards science. We just think that it's maths, physics, bio, and chemistry. So what do you think that, what are the opportunities we can seek? And as you talk about that, we as a human can look all those physics that are going on. So can you just tell us what are the opportunities that the coming youth can seek from this lesson?
Yeah, so I think that math, physics, biology are the fundamentals, but they're not the be-all and end-all. So let me give you an example. My wife is a neuroscientist. She studies the brain. A brain is a very complicated system. It's both a biological system, but you can also treat it like a physical system, but you can also treat it like an applied mathematical system, right? So it's a dynamical system. It's changing all the time. As you're looking at me, your brain is shifting a little bit. And the question of trying to understand how your brain develops, how your brain shifts, this is a whole new area. Now, that kind of, my kind of research is a curiosity research. Her research actually impacts how people develop. Like she can answer the question, is it okay to be using a cell phone all the time? Or, like yesterday we were at a restaurant and I noticed that parents, after they were eating, they gave the kid a little cell phone. They said, play with it. My wife would tell you that's a bad thing because the brain is starting to atrophy from watching a cell phone. So neuroscience is an example of how rapidly we are learning about human biological systems, not as a medical system, but actually as a biophysical system. So when you look at the areas, there are vast numbers of areas. Don't just restrict yourself to classical physics, biology, chemistry are basics. Be strong in them. But when you get time, when you start to look at careers, look broad. All of these areas are mixing and interfacing, and at the interface is a lot of exciting stuff going on. All right?
Good afternoon, sir. I really enjoyed the lecture, but I would like to ask a question.
Sure.
That do you think that universe has any point of center of mass?
Not our universe. The way we conceive of the universe is that there is no center at all in our universe. Or equally, every point is a center. Now, I'm going to give you one analogy to help you sort of think about this, okay? If you take a balloon, before you blow it up, make two marks. Take a marker, put a mark on one side and put a mark on the other side. Now, ask yourself, if I was sitting on this mark and I blow into the balloon, what would I see? The other point will move away. As the balloon expands, the other point will move away. Now, repeat the exercise. Ask yourself, if I was sitting on that point, what would I see? This point will move away. So in that sense, every point in the universe thinks of itself as a center. And every point is not a center because every point is a center. So balloon is a great way to think about it. The way to think about science often is not to get caught up in the deep mathematics. First, think about a simple system, like things that you're used to, bathtubs, glass of water, balloons. And ask yourself, can I create something like that and understand it? And that's how you sort of make progress. Have I answered your question? Okay. Last question. All right.
Good morning, sir. I'm from Bhavan Vidyalaya, New Chandigarh. I really enjoyed your, it was very nice to be here and listening to you. I am very interested in the science and actually in aeronautical science.
Okay.
And my question was, how did the scientists find out that black hole is controlling our solar system and we all are inside a galaxy and in a solar system? How did they even know? It's not that easy, right? I am thinking of something and suddenly it came to mind. How did they even find out? Did that incident happen or something like?
No. This it wasn't. You're absolutely right. It wasn't easy. So it started with over 1,000 years, people were taking measurements of the sky, and they realized that there are stars in the sky that don't change. And then there are objects like planets, Venus, Mercury, they move around. And so over 1,000 years, there were Chinese astronomers, there were astronomers in the Indian subcontinent, more than 1,000, maybe about 2,000 years ago. And there were astronomers later on in the Middle East, in Baghdad, in Damascus, who collected all this information. And then they used that information with mathematics. They said, if I take the data, and I combine it with mathematics to make a model, what would the solar system look like? And so it's a mixture, always it's a mixture of observations and mathematical theory. And then you have to bring them together. And that's how you start to develop ideas and models. And then you test them, because you can come up with a wrong idea, and that's okay. We do it all the time. Yeah.
Hello. एक रेड कलर की कार है सेंट्रो 4014 पार्किंग है प्लीज इसको साइड में कर लीजिए
Answer formally now. But
Sorry,
the,
go ahead.
Professor Arif will be available in the lobby.
Is moving in the opposite direction of the
And people who want to ask more questions can interact with him in the lobby outside.
जो भी स्टूडेंट्स हैं उनके क्वेश्चन बाहर लॉबी में सर 2 मिनट के लिए खड़े होंगे तो वो आप कर सकते हैं क्योंकि स्कूल का टाइमिंग है 12:30 का जाने का.
This is actually like a fire hose being fired out. Yeah.
As someone that's looking to go into research field and all, I've seen a lot of breakage between if you should go into conventional physics and mathematics or go into the quantum side, since it's a very volatile and a new hypothesis that's being built upon. So if you were to recommend one for someone interested, which one should one choose?
Okay. At your point in your life right now, I would say strengthen your physics, because you can't do quantum mechanics until you have a really strong grounding in physics and chemistry. And so I would say strengthen your basic sciences and your mathematics. When you get to university, at that point, start talking to your professors and find out which areas inspire you. This is important. You don't want to spend your life doing something just because somebody else tells you to do it. You have to feel that it's exciting. Do you imagine doing this for 30 years or 50 years? You have to find it exciting. So passion is important. When I interview graduate students, they're talking to me. They think they're answering my questions. I am listening to see how excited they are. I'm listening to see how passionate they are. Because sometimes the problems, somebody mentioned, problems become tough. And then it takes a year or 2 years to solve the problem. What's going to drive you to finish the problem? You will only do it if you're really passionately driven to get to the answer. Otherwise, you'll say, okay, I'm tired now. All right? Can I?
Shall we give him a standing ovation, not running ovation? Thank you, sir. Now it is time for honoring people who have contributed to this event. So, Professor Arif Babul, please stand here. Professor KP Singh, and those who have helped in organizing this event.
I'm just amazed by the
in terms
audience.
of getting students. So I request Dr. R.D. Singh, Professor Sukhmani Balriyar. They are from the Independent Schools Association of Chandigarh. They are representing this association. They helped us to spread the message in the private schools. Then Environmental Society of India, who helped us to get the message to the government schools, represented here by Dr. H.R. Satija and colleagues. Dr. Satija, please come over here.
Oh, I'm glad you enjoyed it. I should turn this off now.
And to do the honors, I request Professor Arun Grover, Professor Suman Beri, Professor Bagla. You heard about big experiments about the universe. Suman Beri here has worked in the largest experiment on Earth, which is in Geneva. So Suman is a part of the Geneva experiment. Professor Suman Beri, तालियां बजा दीजिए इनके लिए. Professor Bagla, Dharamveer, Shri Dharamveer. Professor O.N. Bhargav, Mr. Garg. Professor O.N. Bhargav is a very celebrated geologist. Dr. A.D. Ahluwalia, Professor Ahluwalia, another passionate geologist. Professor Srivastava, Alok Srivastava. Professor Dua, गए क्या? दुआ साहब गए क्या? प्रोफेसर बचावत, प्रोफेसर बचावत, बागला साहब, प्रोफेसर बागला, उनका नाम पहले। प्रोफेसर बागला के लिए सबसे ज्यादा तालियां बजनी चाहिए, क्योंकि प्रोफेसर बागला is the one who caught hold of the speaker and who kind of breathed down our necks कि इसका करना है टैगोर थिएटर में. So प्रोफेसर बागला is. So this was the vote of thanks. We thank everybody associated, everybody present here. We have had over 30 schools, more than 30 schools, more than 700 students, and more than 50 teachers. Thank you.
Thank you all.
Those of you who wish to have a look at it, please go and see. There is a mobile science lab which is also run by SPSTI.